three parts to neuromuscular fatigue. There's the depletion of acetylcholine, a reduced release of calcium ions, and nerve impulse transmissions. So there is a threshold for the amount of acetylcholine that needs to reach the receptor sites on the once it's travelled across the synaptic cleft, and if the acetylcholine threshold isn't reached, then the impulse that's just travelled down the nerve won't be able to continue travelling because there's not enough acetylcholine for it to travel further down the nerve. So cholinesterase breaks down and clears acetylcholine from the receptor sites so that they're clear for for more acetylcholine to travel across the synaptic cleft to the receptor sites when the next impulse reaches the vesicles, so the impulse can be carried on down the nerve cell. So, sliding filament theory. So, calcium is needed for muscle contractions. So, in the sarcoplasmic reticulum, there are calcium pumps, and they can leak and lose calcium ions. This decreases the amount of calcium ions released from the sarcoplasmic reticulum to the muscles and causes the muscle contraction to be weaker, and therefore it appears fatigued to the person, to the athlete. This is because there is less calcium ions. No, this is because if there is less calcium ions, then there's less calcium to attach to the troponin, which causes less sites on the actin to be exposed, which will lead to not all myosin heads attaching to the actin, which ultimately means that the power stroke is weaker and the contraction is not as strong. So the contraction is not as strong, and therefore the athlete will feel fatigued. Action potential is the process that an impulse travels along a myelinated nerve. Sodium is outside the nerve cells and potassium is inside the nerve cells, and the cells which allow active transport to happen are closed, and this is what's happening in diagram number 1. So the enlarged picture is the cell which allows active transport to happen. They're closed, and this is the pump maintaining. This is at rest, so this is the pump when there's no impulse. This is the pump maintaining sodium outside the nerve cell and potassium inside. Then at number 2, when the impulse is sent, the active transport cells open and allow sodium ions into the nerve cells, which causes the depolarization of a nerve cell. So this is on the graph. This is where the arrow from number 2 is pointing. So you've got Na plus, which is sodium ions, coming in and causes depolarization. And then once it's depolarized, then this part of the nerve is depolarized. It will release the potassium ions, which will then repolarize that part of the nerve cell. When the nerve cell has been repolarized, so at number 3 on this slide, the active transport cell will be inactivated, so it will be open, but like the lid will shut so that nothing can go in or out. And then after this has happened, ion pumps then restore the resting concentrations, so they pump out the sodium ions and they pump back in potassium ions. And then these 4 stages are constantly repeated along the length of a nerve, which causes the wave of depolarization to travel down the nerve. So, nerve impulse transmission. A decrease in the pH in the muscles will cause the speed of contraction to be less, so it'll be a slower contraction, and the contraction will be less powerful. So an increase in the concentration of hydrogen ions will increase the acidity, and a decreased pH or increased acidity causes a decrease in the conduction speed of muscle fibres. So with the decreased conduction speed of the muscle fibres, it will decrease the peak twitch tensions, so the contraction's not as strong, and it will cause a corresponding decrease in firing frequency, so there'll be less contractions before they fatigue. And the result of this is there's a decrease in force, and the fast twitch high frequency motor units will drop out and fatigue before the other motor units will.